This is Physics 2212 Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab is to examine the relationship between magnetic field and distance, and overall we are trying to understand the Biot-Savart law. We want to compare the experimental and theoretical values relating to magnetic fields and the distances at which they were taken. As for my results, I saw two things. As the magnometer moved closer to the magnet, the x component of the magnetic field increases. When the magnometer is far away from the magnet, it measures a near zero magnetic field in the x direction. My calculated mu is 3.0339 amperes meters squared, and my n, or the slope of my linear regression line, is negative 2.9387. As for fundamental physics principles, this lab is based on the Biot-Savart law. Ultimately, we are going to combine two different versions of the Biot-Savart law, one for calculating the magnetic field of a bar and one for calculating the magnetic field of a dipole. You essentially combine the two to solve for mu, which is what I showed earlier. The experiment consisted of a phone, a meter stick, some tape, and a bar magnet. The initial conditions were that the phone had to be aligned with the north-south axis, the bar magnet had to be aligned with the magnometer, and the system is the bar magnet, and the surroundings would be everything else. As for the procedure, all we have to do is measure the distance between the magnometer and the magnet at varying values for Bx, in other words, the x component of the magnetic field. Here is my data in accordance with that procedure. From here you can notice that the distance decreasing means that the x component increases in magnitude. The y-intercept of my linear regression line is negative 14.23, which we're going to use for a calculation later. And the b-net was roughly 5.22847 e to the negative 5 Tesla. We can consider this our experimental value for b-net at 45 degrees off axis. Here's my calculation from mu. Remember that y-intercept from earlier? All we have to do is take e to the power of the y-intercept, then set the equation for b bar and the equation for b dipole on axis equal to each other. From here, we know what k is. We know what r is. We assume it to be 1. We know what 4 pi epsilon naught is, or epsilon naught over 4 pi is. From here, we can just solve for mu. This is a value that you insert into your GlowScript code, and as you can see in my GlowScript code, my mu was 3.30339. From here, we can define a function for the dipole formula, where we use the given formula from the instructions to calculate a more accurate version of B dipole. Through some visualization procedures, you can now plot the parallel and perpendicular components of B-net, and you can also show the 45 degree B-net, the one that we calculated earlier, that we measured to be like roughly 5.2284 e to the negative 5. From our model, we found that that magnitude of B at 45 degrees is actually 2.80892 e to the negative 5 Tesla. Now, that's along the same order of magnitude, so that's a similarity, but it's off by a bit. I want to say like 46% approximate error. The reason why our experimental could have been wrong, it could be because of magnetic pollution. We did this inside, and there was like a TV in the area, or our iPads and stuff. It could also be the humidity of the day. You know, a lot of things could have thrown this off. There's too many things to assume that the conditions were ideal. And the on-axis vectors point in the direction of mu, while the perpendicular vectors point opposite to mu, and this is true for both the computational and the experimental findings. Now, what if you hadn't oriented your experiment to compensate for magnetic north, and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would the results have changed? Well, for starters, the results would have been skewed due to interference from the Earth's magnetic field. You know, the whole reason why we're aligning it with the north-south axis is so that we don't have to worry about that as much. Like that, we can truly calculate the B-net at 45 degrees. Now, what if you stuck two identical magnets together, end to end, and you ran the experiment again? How would you expect your measurements to differ? They would likely double, as the combined magnetic fields of the magnets would increase them accordingly. They would also still be in the same direction as before, just stronger, likely double. Conclusions: this was the most hands-on experiment yet, but that had its own trade-offs. You see, it's not as easy to find a spot on campus with ideal conditions. This semester, somebody tried to do this on Tech Green, and even that had some kind of weird magnetic pollution. I honestly don't know what that could have been, but a phone's compass is easily influenced by external magnetic fields. It would tick left every time you brought the strong magnet close to the phone's magnometer. Thank you so much.